Hello everyone, this is Dr. P. Rajkumar, Assistant Professor, Department of Mechanical, KLEF. Welcome to Machine Design course. The topic for today's discussion is design of helical springs subjected to static loads. So the aim of the present session is to make you to familiar the design of helical springs. It is when it is subjected to static loadings. And what do you mean by springs? What are the classification of the springs? What are the terminology involved in the springs? How to differentiate helical springs from the other springs? Everything will be discussed as part of this session. So now let's start the session. So coming to the definition of the spring. So you might have seen these kind of springs in your different applications. Small, even in your pens also you might have seen some springs. In bikes you might have seen cars, and then wherever some loading, high loads are required, trains, you might have seen the many applications you have seen these springs. So what do you mean by spring? So spring is a device generally used to store the energy. So whenever energy is required, then we can release it for that, release that stored energy. And the another definition is nothing but the spring is defined as it is an elastic machine element which deflects under the action of the load and returns to its original position once the load is removed. So it is spring is nothing but it is an elastic machine element which deflects under the applied load, and once the load is removed it comes back to its original position. So that machine elements we will call spring. And as I already told you, the springs are having many applications. The first application, like springs can be used to observe shocks and vibrations, vehicle suspension springs, railway buffer springs in elevators, vibration mounts. So these are the different applications we will be using the springs. Another one is the springs can be used to store the energy. Springs used in the clocks, toys, movie cameras, circuit breaker starters. Springs are used to store the energy. Similarly, they are used to measure the force, like in weighing balances and scales. And springs can also be used to apply the force and control the motion. If you see the cam and follower arrangement, springs are majorly used to maintain the contact between the two elements. For that purpose, we are using the springs in the cam and follower assembly. So these are the different springs in the different applications: suspension application, leaf spring, your tape regarding your cam and follower mechanism, your train springs, your suspension again, different toys application and all. You can see the different springs in the different applications. Now coming to the classification or types of the springs. The first classification is the helical springs, conical springs or torsion springs, laminated or leaf springs or disc springs. So these are the different springs. First one is the classification of the springs is made based on the availability and its functional requirement. So helical compression, the name itself is indicating. So these springs are majorly used in the compression applications. Helical extension, so it is like load pulling. These kind of springs are used whenever the load pulling is the criteria. Then conical springs, you can see in some of the applications where these kind of springs we are using for the compression application. Then torsion springs we can see in the kids toys and all, we can see these kind of springs. Laminated or leaf springs you can see in the heavy motor vehicles, lorries or trucks you can see. Disc springs you can see in the rolling mills you can see these kind of springs to support. So these are the different nomenclature and we will be using in the entire session. So the first one is the spring index. This is the one significant parameter in the designing of the helical springs. It is nothing but it is a ratio of capital D to the small d. Capital D is nothing but mean coil diameter. Small d is nothing but wire diameter. So the spring index is nothing but capital D by small d. E is the Young's modulus, F is the axial force, and there are another terminologies such as free length and solid length. Free length is nothing but whenever you leave the spring unloaded conditions, that entire length will call free length. Then solid length is nothing but whenever you apply load on the compression springs, entire spring coils will be contact with each other. then that length we will call the solid length. And pitch is nothing but it is the distance between the two successive coils from a constant point to another next constant point. That is defined as a pitch value. And you know tau is nothing but shear stress, max is nothing but maximum shear stress, deflection is nothing but it is the this angle between this flat surface and this curvature one. So it is the coil deflection or coil angle we will call. And based on the edge, this based on the end component also they are classified like grounds, whether it is grounded, different conditions are there. Based on the end conditions also the length, free length as well as the solid length will be varying. So I already told you the solid length is nothing but whenever you apply some load, on this spring, then all the coils will come into contact with each other. So this length we will call solid length. Whereas free length, there is no load condition, then this load is nothing but free length. So from this we can derive the free length is nothing but solid length plus maximum compression plus any clearance between the adjacent coils. So this is the relationship between your free length as well as the solid length. And as I told you, the spring index is nothing but capital D to the small d. What is the capital D? Capital D is nothing but mean coil diameter, small I is nothing but diameter of the wire. Spring rate is or stiffness is nothing but it is the rate per unit deflection. So W per load, that means what is the amount of load required for a unit deflection. That value can be indicated using the spring rate or spring stiffness. As I already told, pitch is the distance between the two successive coils. So the pitch can be calculated using free length by n dash minus 1. N dash is nothing but total number of coils or total number of active coils. So the spring index, during the design of your springs subjected to static loading, this C value is very important. Why? Because the spring index itself indicates the relative sharpness curvature of the coil. So how sharp the coil should be there, this value will decide. Suppose we consider the C value less than 3. So what happens? The actual stresses in the wire are excessive due to that curvature effect because it is very sharp. Because of that sharp in nature, the high stresses will be developed. On the other hand, if the C value is greater than 15, the spring itself will be subjected to buckling and tangles. So that's why it should not be considered too low, it should not be considered too high. So from the standards, this value will be generally considered in between 6 to 9 in order to avoid both buckling, tangling and as well as high stresses development inside the your springs. Always remember this value should be in between C is equal to 6 to 9. So I already told you the active turns and inactive turns, because out of all the coils, some of the coils will be attached to the sheeting. They will be attached to some attachment. For example, if you take suspension springs will be, some of the coils will be attached to your bike seat. So that coils cannot be, they won't take any loads. So such kind of coils will call inactive coils. Only the turnings which will take your applied load, such kind of turnings only we will consider during the design. So that one we will indicate with the active turnings. So these are the turnings, like these are called turnings. All these are called turnings. So based on the end condition of your turnings, the total coils we have to consider as well as the solid length as well as the free length. It will vary for the different end conditions. For example, if it is a plain end condition, then the total number of coils we will treat it as N, and the solid length we will consider N plus 1 into D, and the free length NP plus D. So for these are the values for the different other three conditions. So during the designing of the springs for a static loading conditions, we have to consider all these end conditions also. So now let's discuss how to design the helical springs against the static loads. So you consider one spring here. If you see here, This is the one of the tons of the spring. Here if you consider 1 ton, it is subjected to the force F, direct axial it is subjected, another one is this one. Okay, so because of this one it will be subjected to the twisting moment, so which in turn causes for the torsional shear stresses. So first stresses or first stress will be developed inside this is torsional shear stress, another one is the direct stress. So we know that the torsional shear stress can be calculated using torque is nothing but force into your distance. Distance is nothing but diameter by 2. What is this capital D? Capital D is nothing but mean coil diameter. So torque you know already. So what is F? F is nothing but applied load. So by substituting this equation in this your torsional shear stress value, you will get the this tau 1 value is equal to 8 PD by pi d cube. P is nothing but your applied load, D is the mean coil diameter, small d is the your diameter of the wire, and direct shear this is the direct shear stress because of this applied load F. So that is given by load per unit area. So load is F, per unit area is pi by 4 d square. So the combination is tau 1 plus tau 2. So you will get the resultant shear stress that is acting in the spring. So by substituting both these equations in this one, you will get tau is equal to 8 PD by pi d cube into 1 plus 0.5 by small d by capital D. So here this value we will call Ks. It is nothing but your shear stress correction factor. This value is given by shear stress correction factor. So you know capital D is equal to capital D by small d is equal to capital C, that is nothing but spring index. So by substituting all these values in this equation, the entire equation can be written like tau, that means the torsional shear stress developed inside a spring, helical spring, is equal to Ks, torsional shear stress correction factor into 8 PD by pi d cube. P is nothing but load, capital D mean coil diameter, small d wire diameter, Ks is stress correction factor. So by substituting all these values, you can calculate this tau value. If this tau value developed inside the spring is less than the allowable value, then we can say the design is safe. So you can see here, but you already we discussed the sometimes we have to consider the curvature effect also, because the end conditions, whether it is plane or active coils, we have to consider. So if you see, this is the direct stress value, this is the torsional stress value. So whenever the spring is subjected to both of these values, this is the resultant diagram. So here in this equation there is one scientist, he investigated the effect of curvature on the design of the helical spring. So they consider, in order to consider the curvature, he considered the Ks value as well as the Kc. Ks is nothing but the correction factor corresponding to stress concentration, Kc is nothing but the correction factor corresponding to your curvature. So by combinedly this one we can write K. K is nothing but we will call stress factor or wall factor, that is equal to K is equal to 4C minus 1 by 4C minus 4 plus this value. So by substituting K value in this equation, you will get this. By substituting all these values in this, you will get the K value, P is applied load, D capital D known. So like that, using these equations we have to consider theta is nothing but what is the angle of twist and deflection. These are the standard equations. By substituting, your stiffness is nothing but K is nothing but load per unit deflection. So stiffness, once you know the applied load, you can calculate the W value. So it is like that, and this one you can calculate T by J equal to G theta by L. Using that we can calculate the twisting moment value. And here energy stored is nothing but half your base into height. It is the stress strain, the energy stored up to deflection. So it is this value. This value is nothing but half P into deflection, this value. So let's consider one problem here. A helical spring, it is made from a wire of 6 mm diameter and has outside diameter 75. The permissible stress is 350 MPa and the modulus of rigidity is 84. Find the axial load which the spring can carry. So small d is given, capital D naught also given, that is 75 mm. So by substituting this d naught minus d, we will get the mean diameter of the shaft. Once you know capital D and small d, you can calculate the spring index. So once it is known, you know that deflection per active turn they are asking. Find the deflections per active turn. So first we are removing the effect of curvature. So whenever you remove the effect of curvature, it is only the Ks value. So Ks is nothing but 1 plus 1 by 2c. By substituting the c value, which is from capital D by D, in this equation you will get Ks value. Once substituting, that Ks value is equal to tau into Ks into your 8WD by pi d cube. Tau you know, Ks you know, W already it is given. If it is not given, W is not given, they are asking you to calculate the W value only. So W you have to calculate, D is given, small d is given. So from this equation you will get the W value. Once you know W value, you simply substitute in the deflection equation, you will get the deflection value. Deflection per unit turn, they are asking by n value only they are asking. So no need to substitute any this n value. So like that you can calculate the load acting on the spring as well as the deflection of the spring. That is without considering your curvature, and by considering the curvature effect also you can consider by K is equal to 4c minus 1 by 4c minus 4 plus 0.615 by c. By substituting all the values here, you will get this value. And next, tau is equal to K into 8W into c by pi d square. From this again you calculate W value. Once W is known, you substitute that value in the deflection equation. W is known, capital D known, small d also known, G is given already in the problem. So you will get the deflection by n value, you will get the answer. So this is how we have to design the helical springs subjected to your static loadings. So these are the different textbooks that you can consider for your further learning. Thank you.